50 years ago, America sent 12 astronauts to walk on the moon, powered by a machine so massive it required 400,000 mines and the largest rocket ever built. The world watched, conquered space, and then it all vanished. By 1973, NASA ordered the scrapping of Saturn V's blueprints, jigs, and manufacturing lines, erasing the only path that had ever worked. Today, with technology far beyond the era of slide rules and typewriters, we still can't get back. Why we can't go back to the moon isn't just about money or politics. It's about how humanity lost its own secrets. So how did a civilization capable of reaching another world become stranded on Earth? The answer is more heartbreaking and urgent than you think. The scale of Apollo was unlike anything before or since. 400,000 people, engineers, machinists, welders, programmers, and inspectors were pulled from every corner of the country, all working toward a single goal. The budget was staggering. $25 billion in 1960s money, or more than $150 billion today. That meant 1 out of every 30 federal dollars at the peak was flowing into the moon program. Factories in California, Louisiana, and Alabama churned day and night, building the pieces of a machine taller than a football field and heavier than a Navy destroyer. The Saturn V rocket, centerpiece of Apollo, stood 363 feet high and delivered a record 7.5 million pounds of thrust at liftoff, still unmatched by anything flying today. Each launch required a nationwide ballet of suppliers, from steel foundries in Pittsburgh to electronics shops in Boston, all coordinated through a web of contracts and handshake deals. Behind every weld and bolt was a person, sometimes a whole team, whose job was so specialized that a single mistake could ground the entire mission. At Rocketdyne, teams of engine builders memorized the quirks of the F-1's fuel injectors, often relying on tricks learned from the last shift. At Michoud, welders spent years perfecting the art of joining thin aluminum for cryogenic tanks, using touch and sound as much as blueprints. The Vehicle Assembly Building in Florida, still one of the world's largest structures, was built just to house these giants. Apollo's power came from this web. Hundreds of thousands of hands, thousands of shops, and a kind of national muscle memory that could only be built by doing day after day, year after year. But this immense living system was also fragile, held together by budgets, politics, and the will to keep going. In 1973, as the last Saturn V was being readied for Skylab, NASA headquarters issued a set of memos that would erase the physical legacy of Apollo almost overnight. Procurement officers, acting on direct orders, began tagging hundreds of massive jigs, fixtures, and specialized machines for disposal. These weren't ordinary tools. Some weighed over 100 tons, custom-built for welding rocket tanks or assembling engines the size of a city bus. Many bore hand-painted numbers and notes from the teams who had built them, reminders of a workforce that had spent years perfecting their craft. The General Services Administration, tasked with clearing out surplus government property, organized a series of auctions. Auctioneers watched as equipment that once shaped the backbone of lunar missions was sold off for pennies on the dollar or, more often, hauled straight to scrapyards. Over 400 major Saturn V jigs and fixtures disappeared this way. In Michoud, Louisiana, workers recalled the sound of torches cutting through steel that had sent men to the moon. At Rocketdyne, engine assembly rigs were broken down and loaded onto flatbeds, their final destination a mystery to most. Some engineers pleaded to save key pieces, hoping future generations might need them. But the answer was always the same. Storage costs too much, and there's no plan for another Saturn. By 1975, almost every trace of the hardware that powered Apollo had vanished from the factories. What remained was too big to move or too expensive to repurpose. Silent relics in empty assembly halls. The destruction was thorough, irreversible, and, for many who witnessed it, deeply unsettling. A modern NASA engineer sits at a workstation, scrolling through grainy scans of hand-drawn notes. The hunt is on for a missing weld parameter, a detail once passed from shift to shift at Rocketdyne, now buried in boxes of microfilm or, worse, lost to time. Months slip by as teams use AI-driven search tools to comb through what's left of the archives. Sometimes the answer is found in a retired welder's story, not in any official record. The F1 engine, the heart of the Saturn V, was built on these undocumented tweaks. Welders learned to listen for a certain pitch, to feel the vibration in the tool, to spot a flaw before the X-ray. None of that made it into the manuals. When NASA tried to recreate heavy-lift rockets for new programs, they ran into a wall. The Ares 1 booster, designed in the 2000s, shook itself apart during early tests. Engineers traced the problem to dynamic loads Apollo teams had managed by instinct and rule of thumb, knowledge that had vanished with retirement parties and pink slips. On the Orion capsule, weight ballooned as designers struggled to match Apollo's razor-thin margins. The old tricks for shaving ounces off aluminum tanks or routing wires through impossible spaces were missing. Each new project becomes an archaeological dig. Engineers call up retirees, pore over faded Polaroids, and reconstruct lost steps from fragments. The cost isn't just time. Every missing piece means redesign, delay, and soaring budgets. The expertise that once lived in 1,000 hands now exists only in scattered memories and half-remembered stories. NASA's latest attempt to reach the moon, the Space Launch System, has already cost more than $23 billion, and that's before a single operational lunar landing. Each launch draws on a budget that could fund thousands of university research labs or build entire fleets of commercial satellites. Yet, the SLS still relies on technology that's less advanced than what's in most people's pockets. The computer inside an iPhone is over 1,000 times more powerful than the guidance systems that steered Apollo to the moon. But all that processing muscle can't replace the vanished muscle memory of an entire generation of builders. Political support for lunar missions never lasts long enough to finish the job. Every 4 to 8 years, a new administration arrives with its own priorities. Programs are renamed, goals are rewritten, and budgets are slashed or redirected. The result is a cycle of grand promises and abrupt cancellations, each one wiping away years of slow progress. NASA administrators find themselves fighting for survival, not for the moon. While government projects stall, private companies try to fill the void. SpaceX engineers have spent years rebuilding supply chains for even the simplest parts, like high-pressure valves that once came from a deep network of American suppliers. Today, many of those factories are gone, and entire industries have to be reinvented from scratch. Elon Musk has called it a kind of industrial archaeology, where every missing part is a puzzle and every delay costs millions. The irony is hard to miss. We live in an age of supercomputers and instant communication, but can't rebuild what once took a nation to create. China's lunar planners circle a date on their calendars. Before 2030, a crewed landing on the moon. Their program marches forward with steady funding, stable leadership, and a clear timeline. None of the stop-and-go politics that cripple American efforts. Meanwhile, the cost of rebuilding US lunar capability keeps climbing. NASA's Artemis program has already spent over $23 billion, yet even a single operational landing is years away. To truly match Apollo's achievement, experts estimate the price tag would approach $150 billion, more than the entire original program, and with far slower results. Every delay pushes Mars further out of reach. The global race is no longer just about pride. It's about who can build and keep the skills needed to move beyond Earth, before the chance slips away for another generation. Inside NASA, a new kind of specialist has quietly taken root: the Chief Knowledge Officer. Their job is to track down lessons from decades past, collecting stories, technical fixes, and even the unwritten rules that once kept missions on track. AI-powered search tools now crawl through millions of pages, pulling up lost blueprints and forgotten memos. Before retirement, engineers are called in for mandatory exit interviews, asked to share not just what they did, but how they did it. Some lawmakers have even pushed for decade-long funding locks, hoping to shield projects from the next political storm. These efforts don't promise a perfect memory, but they offer a fighting chance. The hope is simple: if the next great leap depends on what's remembered, maybe this time less will slip through the cracks. In 1973, NASA issued formal orders to scrap more than 400 unique jigs and fixtures used to build the Saturn V, ending the era that had put 12 Americans on the moon. The documentary has shown how this deliberate dismantling erased not just hardware, but also irreplaceable knowledge held by over 400,000 engineers and workers. While extensive documentation existed, much of the expertise was never fully recorded. And today, even with over $23 billion spent on the space launch system, the technical and institutional gaps from the Apollo years persist. Some original engineering records remain lost or classified, leaving unanswered questions about recreating certain methods. As China targets a crewed moon landing by 2030 and NASA implements new knowledge preservation programs, the evidence is clear: the moon is not out of reach because of physics, but because of choices. The real lesson is that a civilization's greatest achievements are fragile, and once forgotten, they are far harder to reclaim.